So in this video, I wanted to talk to you about shear and bending moment diagrams along with their practical applications. So if you've looked at any large-scale structures, you've undoubtedly seen a beam. What actually qualifies as a beam? Well, traditionally, it's going to be some structure that actually looks like it's very kind of small in the cross-section relative to how long it is. It's traditionally going to have a uniform cross-section across its entire span. But the real thing that really classifies a beam is it's going to be intended to be loaded in a manner that's always perpendicular to it. And those loads might not be applied directly. They might be transferred through some other aspect of the structure. For example, in a house, you might have subflooring or decking that actually takes the load of the walls and your furniture and all of your walking and transfers it ideally to the beams and loads them in a perpendicular fashion. I know there's not a lot of basements in Texas, but if you ever walked in a basement beforehand, you've undoubtedly seen kind of the array of 2x8s that serve to actually be load bearing in your home. So when you actually classify beams, in the textbook at least, you can classify them in two different ways according to the way that they're supported. Over here on the right, we have a beam that's supported by a pin connection and a roller connection. We know very well now that this pin connection has two unknowns in the reaction structure associated with it. Namely, it can oppose horizontal motion and vertical motion. So it will have an unknown X and Y component. As we mentioned, since all the loading is traditionally going to be perpendicular, we'll see that we really don't need that X component. And of course, the roller connection can oppose motion only in the vertical direction or normal to the actual point of intersection between the two surfaces. So the reason that the book even spends time describing this is this naturally is a statically determinate loading configuration because there's three unknowns and we can write three equations of equilibrium. So it's a good textbook problem. Another kind of name that they give to a beam is you can have a cantilevered connection, and this is a common name out in the real world, unlike these simply supported beams. And that just basically means you have a beam that's fully fixed at one end. So whatever the support structure is at one end, it can't move left or right, it can't move up and down, and it can't rotate. But the rest of the beam is totally free, and that's called a cantilevered beam. So what we're going to be doing in this section is developing an expression to find out how the actual shearing force and bending moment, which are going to be the only two internal forces that exist inside this beam, vary across the span. So we know already how to take any point along that, pass a section, do method of sections, and solve for the shearing force and the bending moment. But the question is, can we come up with an expression of how they vary across the entire beam? And the reason that we want to do that is very valuable. In fact, it's a necessary tool in order to design cross sections for a given anticipated loading condition. So these, what we're actually going to be solving for are going to be the shearing force internally as a function of x, where x is the distance measured along the beam, along with the bending moment as a function of x, where x is the distance along the beam. So we know how to find it at one point, as I mentioned previously. How are we going to find it as a continuous function? We don't want to do the work and just sample a bunch of different points. The way that we're going to do it is based upon knowledge that these two functions are continuous unless two things happen. One, you have a concentrated load applied at a point, or two, your distributed load has a discontinuity. And in either of those cases, what we're basically going to do is identify those points, and we're going to develop and do free body diagram analysis, the same type of static analysis that we've been doing up until now, on the left and right of those points, under the assumption that unless we're touching one of those, these are going to be continuous functions. So if rather than just draw or pass the section at 3 meters, we call the point where we're passing the section x, and we work the whole problem as a function of that variable x, what we'll find is we're able to get continuous expressions for certain simplistic loading conditions, and then we can actually draw those functions, which are going to be called our shear and bending moment diagrams, and we can kind of describe certain summary characterizations of them, like their maximum value and so on. Maximum value, of course, from a design point of view is going to be the thing that matters the most. So in the next video, we'll get a chance to actually apply this technique to a real problem.